Hi, Dr. Lyons here, of course. This is a supplemental lecture on the topic of tensile properties and mechanical behavior of metals. Okay, so let's talk about tensile deformation. And properties of metals. Start with a couple of schematics of what the test equipment looks like to determine mechanical properties of metals. This is a photograph of a machine that's called a universal test machine, and it's universal because it's capable of testing materials both in tension and compression. And in this particular machine, there's a sample that's right here, and it's gripped between two grips. There is a load cell that measures the force that's attached to this crosshead. And in this particular machine, this crosshead is attached to some screws, some giant screws in these two columns, so that when the screws turn, the crosshead moves up or down. This schematic shows the moving crosshead on the bottom. Both designs are probably equally popular in industry in terms of machines you buy. But again, there's a load cell that measures the force that is applied to the specimen when the crosshead is moved down. And this is a device called an extensometer. It's a little gauge that clips onto the sample, and it determines how much the sample stretches, or it measures how much the sample stretches. And here's a zoom in on a typical tensile test specimen. You see that the area of the sample, or the regions of the sample that are actually gripped by the upper and lower grips, are larger in diameter than the test specimen, and that's so that we don't get failure of the sample where the grips bite into the piece of metal. And so there's a reduced gauge section, and the gauge length is the length of the sample that is held by the extensometer. So the load cell measures the force, and the load cell measures the force, and the extensometer measures, I'm not spelling well today, measures the change in length of the gauge length. Okay, so if we take a piece of metal, for example, a wrought aluminum sample, and we put it in the test machine and we pull it to failure, we're going to get a graph of force versus change in length from the load cell plotted against the extensometer that has initially a linear region, and then the stress or the force is going to increase more slowly with change in length, and at some point the force is going to drop and we get fracture. So we can divide this up into basically three regions. Region 1 is the initial linear region. Region 2 is this curved region, and region 3 is actually a point that's fracture. So labeling my graph, this first region is where we have elastic deformation only. The second region, the sample has both elastic and plastic deformation in it. And the final event is fracture of the sample, where it actually breaks into two pieces. Now, that's what's measured. If I have a different sample size, then I'm going to get a different response in terms of the force versus the change in length. With a different sample size, I'm going to get a different force versus delta L response. So to normalize the test results so they're independent of sample size, we use the concept of an engineering stress and strain. And so the engineering estimates of stress and strain are used to normalize the data. And so engineering stress, as you may recall from your solid mechanics classes, is the force over the original area. And engineering strain in uniaxial tension is L minus L0 over L0. That's the instantaneous length minus the original length over the original length, which I always just generally write as delta L over L naught, where the subscript O represents original or undeformed value of the area or the length. So I can go back to my force delta L curve, and if I divide the force by the original area, I get stress on the y-axis, and if I divide by the length by the original length, then I get strain on the x-axis. So now I've got a stress-strain diagram that when I rescale the axes for that calculation, I get the stress-strain curve. Okay, so let's talk about the properties in regions 1, 2, and 3, elastic deformation, elastic plastic, and fracture. Section 1, elastic properties. Okay, the big one, the one that we all love, is the elastic modulus. And elastic modulus is a measure of stiffness. Elastic modulus measures stiffness. And to calculate that, we find the change in stress divided by the change in strain in region 1. So going back to my picture, the elastic modulus is the slope, change in stress divided by change in strain, of the initial loading curve. Now, the reason it's called the elastic modulus is because, elastic, is because in this first region, if we were to graph stress and strain, for most metals it's linear, but it's elastic in that the stress-strain response increases during loading, but if I stop and then unload the sample, the deformation is recovered when I remove the load completely. So I could just take the sample, I could stretch it, and then unstretch it. And I could do it just a little bit and then take the load off, and the strain is going to return to zero as long as the material is behaving elastically. A second material property is Poisson's ratio. And this measures compressibility. In conjunction with the elastic modulus. It's a measure of stiffness as well, but stiffness in the in the sense of compressing instead of compressing in a transverse way. And nu, the Greek nu, is the symbol for this, and it's equal to the ratio of the strain in the y direction divided by the strain in the z direction. And so what I'm talking about here is a sample whose coordinate rate is oriented such that the z direction is up and the y direction is to the right. If this is an isotropic material, then that ratio is in the stretching in the, or thinning in the x direction is the same as in the y direction. So that's the definition, and what happens is when the sample is stretched, it gets longer. I'm going to exaggerate this here. Z, Y, X. So if I take a sample and apply a force or stress to it, it's going to get longer and thinner, and the Poisson ratio gives you an idea of how much thinner it gets for every increment of extension. Now, to measure this, we need to be able to measure the strain in the y or the z direction. Therefore, what we actually need is another extensometer. We need some way to measure that change in diameter. So we need a transverse extensometer. Okay, these are the two main elastic properties that we can pull out of a tensile test machine with the right equipment. Let's talk about region 2, where we have plastic deformation occurring. And plastic deformation is often considered the failure of design. If a metal sample is deformed permanently, that's usually considered a bad thing. Unless you're trying to make a part. And really, plastic deformation is just the beginning of a manufacturing process like forging. Manufacturing. And so let's talk about the different aspects of this. First is yielding. And yielding is the point where permanent deformation begins. This is the beginning point for permanent deformation. Okay, so let's draw a little stress-strain diagram again so we can talk a little bit more about this. Stress versus strain, and got the region where it's linear elastic, and then so let's do it this way. Let's say we started with a sample that was not under load. We start to increase the stress. We eventually reach a point in most ductile materials where the stress-strain curve bends over. If I was to unload the sample at that stress right there, then the strain would be recovered at a rate proportional to the elastic modulus. So here I'm loading it, and here I'm unloading it. And the slope of that unloading curve is the same as the initial slope of the loading curve. The strain that I get that's permanently part of the specimen now is epsilon P. And the total strain just prior to unloading would be obtained from what's that, a horizontal drop there. So here in this picture, epsilon T is the total strain. At stress, let's call that sigma 1. So I'm going to label this sigma 1 is that corresponding stress. And the amount of strain that's permanent or plastic is given by epsilon P. And the epsilon E, which is the part that's recovered, that is the elastic strain at sigma 1, and that is just going to be the difference between, so the total and plastic strain. So epsilon E is epsilon T minus epsilon P, and should be about equal to sigma 1 over E. Now, when does plastic strain start to accumulate? That actually occurs at a point called the proportional limit, the proportional limit. We can use the letter P for that. And P is defined as the stress at the elastic-plastic transition. It is the stress at the elastic-plastic transition. And it's really nearly impossible to actually measure. In a stress strain diagram, it occurs, in this particular schematic that I've drawn right here. I'd say that's probably somewhere around there. P is the stress at the region where the sample goes from being linear elastic to starting to accumulate plastic strain in addition to the elastic strain that is associated with the applied load. It's really hard to measure because that transition is kind of gradual, because in a polycrystalline metal, some grains yield before others, and it's really pretty tough. And so we don't usually use the proportional limit as a material property because it's hard to determine. Instead, around the world, we, at least in the United States predominantly, we use a definition for yielding beginning at the 0.2% offset yield stress. So 0.2% offset yield strength. Sigma y is a commonly used material property to define when yielding occurs. And sigma y is the stress at a permanent strain, epsilon P, equals 0.2%. And that's the way we write it. So that's a strain at 0.002, a permanent strain of 0.002. So the way somebody calculates sigma y from a stress strain diagram, stress strain, is find on the strain axis a strain of 0.002 and draw a line parallel to the initial slope. And this was always a challenge. Maybe you can do better with some software. And where your line, I didn't do a very good job, but I think it's pretty parallel to that, where that line intersects the stress strain diagram, gives you the yield stress, the 0.2% offset yield stress. So the procedure for finding the yield stress, if I'll summarize that, is you draw a line from epsilon P, it's actually just strain epsilon of 0.2%, and you draw this with a slope equals E. That's what I did right there. Then the second step is you find the intercept with the test plot, and then you read sigma y from the stress axis. Okay. Now, the next sort of interesting event is in region 2 is called necking. And necking is a rapid reduction of the cross-sectional area. It is a rapid reduction of cross-section area, and it occurs in one section of the gauge length. Let's see, so here is a sample. This happens to be a piece of plastic, but this occurs in metals as well, where the sample was tested in tension and some necking has occurred right here. So you can see that the sample has gotten thinner at one particular section. That's going to happen in metals as well. This sample has been tested to fracture. This was a metal sample, but you can see that the cross-section is fairly constant along the length, but in one region it starts to neck down towards a point. All right, so in terms of where this occurs on the stress-strain diagram, linear elastic, yielding, and then the point where the curve, the slope of the curve starts to drop is where necking occurs. It starts there. Okay, and the stress that corresponds to that particular event is called the tensile strength, often referred to as the ultimate tensile strength. I think I usually use the word, the letters TS for that. Some folks will write it as UTS. So, but tensile strength works good. That's material property. And tensile strength is the maximum engineering stress. Engineering stress. And it corresponds to the stress at onset of necking. Now what happens in a metal is, remember, necking is a reduction in the cross-sectional area. And so as the area goes down, the force required to stretch the sample also drops. So as A goes down, F required to stretch the sample goes down. Okay, so therefore, since we're plotting stress versus force over original area and not the actual area, that curve, that stress versus strain curve drops at the point of necking. Now, in reality, in terms of what's the real true stress that's going on in the sample, something that's not based on an original area, which is no longer truly accurate, the reality is that the true stress in the neck continues to increase. But what's happening is that A goes down faster than the force goes down. So the true stress actually increases in the neck. So this leads us to when deformations start to get large, the concept of true stress and true strain start to become important. So true stress is defined in tension as the force over the instantaneous or actual area. So AI is the actual area under load. And true strain is defined as the natural log of Li over L0, where Li is the actual gauge length. Up to necking, we can actually relate true stress and true strain. So up to necking, we can use the constant volume equation. Or assumption. And that says that the original volume is equal to the instantaneous or actual volume. And under uniform deformation, which is up to necking, then A0 volume, the first volume is just the area of the sample times its length, and that's equal to the area at any particular time times the actual gauge length, like that. Okay, and so schematically the way these would actually look on a stress strain diagram, I'm just going to write stress here and strain here because I'm going to plot two different definitions of those. So my stress strain curve that we've drawn before may look like that, engineering stress versus engineering strain, whereas my true stress strain curve, it's going to follow initially about the same slope when the strains are small, but we're going to see that the true stress is going to actually be higher than the than the engineering stress. So this is the engineering stress versus strain curve. This is the true stress versus true strain curve. Both have the same slope, but as the initial area and initial length start to differ significantly from the as the instantaneous or actual area and length start to differ from the original dimensions, then the true stress and strain curve starts to deviate from the engineering one. Now, in both cases, there's this thing that's going on right here where the stress strain curve is rising. And this increase in strength with strain is called strain hardening. Increase in strength as the strain goes up is called strain hardening. So strain hardening is an important concept. Okay. Now, get towards the end here. Let's talk about what happens during fracture. So the steps that lead to failure in metals are some accumulation of damage in the sample. Little voids form as the metal starts to pull apart. Then we get some crack formation. And then finally the cracks that form propagate. So we get crack propagation. So two material properties of importance here are associated with fracture are ductility and toughness. So let's talk about ductility. And ductility is defined in this context as the permanent strain to fracture. Permanent strain to fracture. Let's put that in quotes because there's actually some more precise definitions. One of the more precise definitions is called percent elongation. And percent EL is the final length minus the original length over the original length times 100%. And the other definition of ductility is the percent reduction in area. Percent RA is defined as the original area, the original area minus the final area over the original area times 100%. So we can actually measure the final area as the cross-sectional area at the fracture point. AF is the cross-sectional area at fracture location. So after the sample breaks, I can take a micrometer or a caliper and I can actually measure the dimensions of that fracture and get the actual cross-sectional area at the fracture point. So usually when we're talking about ductility, the percent reduction in area is what we want to use because this final gauge length is not so great. If we were measuring it with a clip-on extensometer, it's not such a great measure of ductility because once necking begins, we get a lot more deformation in the metal than we do at that point than we do over the average length of the sample. So percent elongation is really only a good measure of ductility if the deformation is uniform along the length. And since when necking occurs, the deformation is not uniform along the length, that's not such a great thing to use, but sometimes it's all we've got. And we just make the best we can do with it. Okay, so here's a couple of sketches. Something that is a sample that's 100% brittle is going to have basically no reduction in area at the fracture point. I'm going to leave a space right here, and I'm going to come over here, and something that a sample that actually necks next down to a point would be 100% ductile. So this represents something that's 100% brittle. Some metals like that, 100% ductile. It's kind of a theoretical construct, but you know, if you've ever pulled on some like Laffy Taffy or something, maybe it'll neck down to a little point. So there are materials like that. Most of the metals of structural importance are somewhere in between, and so what we actually see is a sample that necks down a little bit, but not to a point before it breaks. And a lot of times the fracture will look like a cup and a cone type shape. So this would be moderately, or something that has moderate ductility. Cross section of a sample. So the final area is finite, and it's not zero, and it's not the same as the original one. It's something that can be measured. So that's what the samples look like. In terms of the stress strain diagram, if you were to compare the stress strain diagram for a ductile and a brittle material, a brittle material isn't going to deform very much before it breaks, and a ductile material is going to stretch a lot before it breaks. Now, most engineers are going to say that it's brittle if the percent elongation is less than 5%. Say it's brittle if the percent EL is less than 5%. That means that basically the plastic strain is less than 0.5. So if we would find that, there's a missing zero there. 5% is 0.05, right? Okay. So if that's going to be somewhere around here, 0.05. And the last property in this supplemental lecture is toughness, also associated with describing the material behavior all the way up through its ultimate fracture. And toughness is defined as the energy required for fracture. How much energy can be absorbed without the sample breaking. And on a volume-specific basis, this is the area under the stress-strain curve. So if I graph stress versus strain, and if I have some sort of stress-strain curve, the area under that curve is the toughness, which is the integral from 0 to the final strain, given as the point on the associated with fracture, of sigma d epsilon. So it's a specific energy. So I hope this lecture was helpful, and I will see you next time.